All right, good morning, guys. Today we're going to be covering 10.7 nets, cross-sections, and solids of rotation. Our learning target today is I can determine nets of a 3D figure, determine the shape of a cross-section, and rotate 2D figures around an axis to create 3D figures. Let's go ahead and get started with nets. A net is a diagram of the surfaces of a three-dimensional figure. So it's just the diagram of all the surfaces, all the outside-facing portions. These two-dimensional surfaces can be folded to form their three-dimensional figure. To identify a three-dimensional figure from a net, look at the number of faces and the shape of each face. So again, think about these nets as flattening down a 3D box. If I have my 3D figure and I need to break down that 3D figure, pretend it's a box, and what would happen if I laid it all flat? That's what we need to be thinking about when we're dealing with nets. So, let's complete each row of the table, express the circumference of the cylinder as a multiple of pi. So we're just going to go ahead and fill out the type of solid. We'll draw an example if we need to. We'll list the number of faces, and we'll draw a net if we need to. So getting started, the first figure that we have here is this example. If I look at this, this is a prism because I have two different bases, and they're all connected by segments. And these two bases, of course, are congruent. So since all the bases are rectangles, all of the faces here, we're going to say that this is a rectangular prism. And if I want to count up the number of faces, I just count the number of sides that are facing the outside. So looking here, I have 1, 2, 3, 4, 5, 6. So a total of 6 faces. Let's try another. This time, we have a triangular prism, and we need to draw an example of it. So to draw an example of a triangular prism, I'm first going to start with my two bases, triangles. And I'm just going to connect each vertice of these two triangles together. And we'll create a triangular prism. Of course, it's a triangular prism because both bases are triangles, and everything else is made of rectangles. They tell us that for the faces, we have 5 total faces, a pair of congruent triangles, that's 2 of them, and then 3 rectangles that are created from that. So if I were to actually flatten out this triangular prism, it would create a nice, perfect net with 3 rectangles and 2 triangles. So there's one of my rectangles, and then there's the other 2. And then, of course, we have the 2 triangles on either end. All right, next up. This time we have this figure over here as a net, and it says a rectangle and 2 pairs of congruent isosceles triangles. So these 2 triangles are congruent, and these 2 triangles are congruent to each other. So again, we have a total of 5 different faces. Now, if I were to fold these all up, they would all meet at a single point right in the center, which would mean that this is either going to be a cone or a pyramid. Since our base is not a circle, it must be a pyramid. But what type? Well, it goes back to what type of shape the box is, the base is. And in this case, the base is a rectangle. So therefore, this is a rectangular pyramid. If I want to draw an example of this, I'd start by drawing in a parallelogram, and then I just put one single point above the parallelogram. With that single point, I draw all of my segments to it, all of my lateral edges, and it will create a nice rectangular pyramid. Next up, we have a cylinder, and they give us an example of what a 3D cylinder would look like. How many faces are on this cylinder? Well, we have the 2 circles, the top and the bottom base, so there's 2 there. And then the center, this lateral area. Well, that lateral area is just one big rectangle. So therefore, we have 3 different faces here. As for our net, of course, I'm going to have 2 circles on either side of a very large rectangle. So here's my rectangle, right in the center, and then I have 2 circles on either end. All right. Next up, we're going to be talking about cross-sections. Recall that a cross-section is a region of a plane that intersects a solid figure. Cross-sections of three-dimensional figures sometimes turn out to be simple figures such as triangles, circles, and rectangles. When you're thinking about cross-sections, think about the game Fruit Ninja. When you are playing Fruit Ninja, the object of the game is to cut as many fruit as possible without cutting a bomb, or else it explodes. So when you're cutting fruit, what happens is you cut it in half typically. And when you cut it, it creates a shape on one side of the cut. What that shape is called is a cross-section. So these shapes in here, these are cross-sections. And that's why those shapes are typically so simple, such as triangles, circles, and rectangles. Is because when we cut it with a plane, it's going to create a two-dimensional figure. And that 2D figure is always going to be either a circle, rectangle, or triangle. Or it can be a trapezoid if needed. It can be any 2D shape that can be created from that cut. So that's what a cross-section is. It's just what shape is created from cutting that shape. Let's go ahead and try out some examples. Describe the cross-section of each figure. Compare the dimensions of the cross-section to those of the figure. So, starting off, we have a cylinder here, and we see that we have our plane that cuts the cylinder right through the center. Now, with that, this would be our cross-section, where it cuts, that plane, the shape that's created from this cut. And we're going to compare that cut to every other shape that we see here. So if I move this plane up or down, would it create the same cut? And the answer is yes, because this is a cylinder, and the bottom base and the top base are congruent. That means that the circle from the bases will be the same throughout the entire thing. No matter where I cut it from, I'll get the same exact circle. So therefore, you should always ask yourself, what shape is this? And in this case, it's a circle. So therefore, our cross-section is a circle. And again, if I move this plane up or down, it will not change the shape of the cut. So therefore, the cross-sections do not change for planes that are parallel to the one that we just cut. Let's try out another one. This time, we have a cone. And with our cone, it's being cut by this plane. Now we can see that this plane is going through the vertex of our cone, the top point up here. So we ask ourselves, what shape is created? And here, we can very clearly see that we have a triangle. So therefore, the cross-section of this shape is a triangle. Now, if I have a triangle as my shape, would it change if I move this plane forward or backward? And the answer is yes. Because if I move it from this vertex, then I'm no longer cutting at the diameter, but I'm cutting at a chord. And when I cut at a chord, it's going to be a shorter bottom base for the triangle. So therefore, the area of our triangle would change, which means that our cross-section of the triangle would change. So therefore, yes, the cross-section would change if I made it from another cut. We have another cylinder again. This time, instead of a horizontal cut, I'm doing a vertical cut. So what shape is created? Well, in this case, we can see that we have a rectangle that's created. And again, if I move this plane forward or backward, and it's no longer cutting through the diameter, it will change the dimensions of that rectangle. So that cross-section, the area of this cross-section, would change based upon which segment I'm cutting from. If my plane's cutting from the diameter, of course, it'll be the biggest rectangle it can be. But if I'm cutting from a chord that's closer to the edge, it's going to be a smaller rectangle because the height won't change. However, that width would, because it's a smaller cut that we can take from. All right, our last topic for today is generating three-dimensional figures using rotations. We can generate 3D figures by rotating a two-dimensional figure around an appropriate axis. Generally, this will be the x or the y axis. Now, as you get further and further advanced in mathematics, you may be rotating around a z-axis at sometimes, or any other axis that they may give you. They may say, oh, rotate around the line y equals x, or something along those lines. So keep in mind, it's going to be typically x or y axes. We're not going to change that for you guys, so those are the ones that you guys will be seeing. Now, if I were to swing something 360 degrees, what is the base that would be created? So for instance, if I were to rotate this line 360 degrees, what base shape would be created? Well, anytime that you see 360 degrees, you should be thinking circle. Because if I'm rotating something 360 degrees, that means that's going in a full circle. So therefore, it will have a circular base. And that's very key for us, because as we go through these problems, every time that I rotate one of these, it's going to go in a circular motion, thus I should have a circular base. So here's our first one. Describe and sketch the figure that is generated by the rotation in three-dimensional space. We want to rotate the right triangle around the y-axis. What shape does it form? So we have our right triangle here, triangle ABC, and we're going to rotate it around the y-axis. If I were to do that, point C is going to go all the way around over here and then come back to its starting point. Point A won't move, and point B won't move because they're both located on the axis. Only point C is moving. So therefore, if it goes all the way around and comes back to where it started, it would create a cone, a nice, solid, circular cone. Now, from here, they give us dimensions. They say segment AB is equal to 8, so that'd be our height, and segment BC is equal to 6. That'd be our radius. What is the volume of the 3D shape? So the volume formula for any three-dimensional shape that ends in a point is just 1/3 big B times h. Now in this case, big B is a circle, so I'd use the area of a circle, pi r squared. And the height is AB, 8. So therefore we have volume is equal to 1/3 times pi times 6 squared times 8. 6 squared will give me 36, times pi will give me 36 pi. 36 pi divided by 3 is 12 pi. 12 pi times 8 will leave us with 96 pi centimeters cubed. Now, would the volume change if you rotated the triangle around the x-axis? What do you think? Instead of rotating around the y-axis, I rotated around the x-axis. Let's go ahead and test out your hypothesis. So, this time, we're going to keep the same dimensions, but we're rotating around the x-axis. So, since points B and C are on the x-axis, they won't move, but point A will swing around to the other side, and then back to where it started, because again, it's going 360 degrees in a circular motion. So therefore, again, from our last problem, we have 96 pi centimeters cubed. We're going to test that hypothesis, and point A is the point that's being swung around. Now, in this case, our radius is now 8 centimeters, and the height of our cone is now 6 centimeters. Plugging into the volume of a cone, we have volume is equal to 1/3 pi r squared times h. R is now 8, and h is now 6. 8 squared is 64, times pi is 64 pi. 6 divided by 3 is 2. 64 pi times 2 is 128 pi centimeters cubed. So, do they have the same volume? The answer is no. So the hypothesis, if you chose no as your hypothesis, you were correct. And the reason why is because we're not squaring the 6 anymore, we're now squaring the 8. So just squaring that specific number changed our entire answer. If this wasn't squared, then of course we would have gotten the same answer. But because the r value is squared, that changes our answer completely. Let's go ahead and try out one more of these. And again, yes, the volume would change, and the main thing that you guys need to worry about is that the axis of rotation is important. It does matter which one that you rotate around. If you rotate around the wrong axis, of course you guys just saw that you would get the wrong answer, because we saw that the volumes would not be the same in that case. Here's our next one. We want to rotate the rectangle around the y-axis. What shape do you get? So if I rotate around the y-axis here, I know that only points C and D will move because they're not on the y-axis. They're going to move 360 degrees, so a full rotation of a circle. So it'd create a nice cylinder for us. If AB is equal to 10 centimeters and BC is equal to 3 centimeters, what is the volume of the 3D object? Well, since this is a cylinder, our volume formula is just big B times h. Big B is a circle, so I'd use pi r squared times h. Since AB is equal to 10, that would be our height, and BC being 3, that would be our radius. So volume is equal to pi times 3 squared times 10. 3 squared is 9. 9 times pi is 9 pi. 9 pi times 10 is 90 pi centimeters cubed. And that's the volume of our cylinder. Our final problem of the day is to determine which shape would be created if we rotated this circle around the y-axis. Think about food. If you rotate this circle around the y-axis, since none of these points are on the y-axis, they're all moving. So this would create a donut. You go in a perfect circle, just like the planets do around the sun, creating a nice donut for us. So that's the shape that would be created. All right, guys, thank you so much for watching today. If you have any questions, please let me know, but have a great rest